This video is about the limit definition of the definite integral. For our notes, we'll recall that to find the actual area under a continuous curve on an interval from a to b, a closed interval, we define it the following way. We say a for area equals the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I star times delta x. Okay, that's kind of a mouthful, but we've seen that develop. That was a previous video where delta x was defined for convenience as b minus a over n. That would turn the interval from a to b, where we are here, into n equal width intervals. And then for convenience, we said we'll pick a sample point in each interval, denoted by x sub I star. And we said for convenience we could define that to be a plus I times delta x, which would give us the right side boundary of each interval. It's just a convenient calculation. Really, this sample point, x sub I star, could be anything in the interval, either side, either boundary, or anything even in between. However, as an area, we restricted f of x to be greater than or equal to 0. Now, when I say restricted, we didn't actually make a big deal about this when we were discussing areas. It just so happened to be that the examples we were looking at were this way. And so you'll find that typically in the context of area, because area is typically understood as a positive metric or measurement. As mentioned in that video, this calculation, defined here for area, also works to compute distance. We mentioned that distance is really rate times time, which is kind of like a base times height, and you can use the same setup with this limit involved to calculate distance as well. Let's now add a definition in the mix here. The sum that we were just using within our limit, if you think back a step here, that is the sum from I equals 1 to n of f of x sub I star times delta x. Okay, so we just used that above in our area calculation. But if we take that sum and just kind of extract it from that area calculation for a second, and without the restriction that f must be positive, which we just mentioned in the previous definition or recollection there, then this sum is called a Riemann sum, named after German mathematician Bernhard Riemann. And in other words, our definition for area, which we just wrote and recalled above, uses a type of Riemann sum where the function is stuck being greater than or equal to 0. In other words, our area calculation is a Riemann sum, but Riemann sums are actually more general, and when you don't have to restrict the function to be greater than or equal to 0, you can use this same calculation for all kinds of applications, as we will eventually see here. The point is, a Riemann sum is a more general sum where we've taken a certain case where the function in it is greater than or equal to 0 to define our area or our distance. Let's continue to another definition where we'll say that if f is a function defined on the closed interval from a to b, then the definite integral from a to b is as follows. Now there's a lot of notation here. I'm going to read through slowly. First of all, the symbol used for this integral is like a stretched out S. It's stretched out as an S because it actually stands for the word sum, which is what we've been dealing with in this context here. Okay, so this stretched out S, which typically has in the definite integral, it has a subscript and a superscript. So we've defined those as a little a and a little b in those places respectively. And then after that notation, we have f of x, and then we have this dx following it. All right, so that notation is referred to as the definite integral. Now what we're saying here is that it is equal to the limit as n approaches infinity of this Riemann sum. So we just understood that this familiar sum, which was used in the context of area, but when we restricted the function to be greater than or equal to 0. More generally speaking, if that function is not restricted that way, it's called a Riemann sum. We just talked about that above. Well, the limit of that as n goes to infinity is the limit definition of this definite integral. It's what it means. But we're still going to use delta x as b minus a over n, and x sub I star as this a plus I times delta x. They're just really convenient definitions, and it turns out they're not the only options, but if they're convenient, why not use them? Now, if this limit exists, as we just wrote above, then we say f of x is integrable on this closed interval from a to b. Let's pick apart this definite integral notation a little bit more with some vocabulary. So as mentioned, it is this kind of elongated, stretched out S-looking figure with a subscript after it with an A and a superscript B. And those values are called the bounds or the limits of integration. So you could say the subscript A is the lower limit, or the lower bound sometimes it's called, and then the upper superscript B would be, of course, the upper limit. And of course, those values come directly from the interval on which this function is being considered. So we talked about being on a closed interval from a to b. Well, that's exactly what those boundaries are. Now the function itself, f of x, following this integral symbol, when it's written in that context following the integral symbol, is called the integrand. And simply put, it's the function that is being integrated. And then this dx, which we see at the end, we've already explored that in the context of derivatives, even the differentials. But in this case, for now, we're simply going to use that as part of this, package deal notation. It goes with the integral. But I want you to notice that it's dx, and that variable matches the independent variable of the function, which means we can just call that the variable of integration. And that variable will match the variable in the function, the independent variable in the function. Let's also consider some properties of a definite integral. There are several. We'll read through them carefully. The first one is that the integral from a to b of f of x dx is equal to the negative integral from b to a. So notice what happened here. When you swap the limits of integration or the bounds of integration from a to b instead, now we're going from b to a, you can do that, and the cost is you have to put a negative sign out in front of the integral. You could switch them either way. If the negative sign is starting out there, then you could take it away and switch them. The point is, it's kind of like just that -1 factor that when put out front will switch those bounds. Secondly, we'll say that the integral from a to a of f of x dx is 0. When the bounds are the same, the value of the integral is 0. Thirdly, the integral from a to b of c times dx, where c is just a constant, is equal to c times the quantity b minus a. Now, visually speaking, there's a nice way to, I think, grasp this, and that is if we just take a coordinate plane, and let's say the value c is some y value here, and so the function y equals c, or f of x equals c, that would be just a constant function, a horizontal line. But if you're integrating that from a to b, and you throw a and b down on a coordinate plane with this here, then remember, we said that if your function is positive, which we're presuming c is in this little illustration here, then the integral would be like the area under the curve. Well, in this simple picture, that's the area of this rectangle defined from a to b and 0 to c. Well, the area of a rectangle is just base times height, which is exactly what this formula is conveying. C times b minus a would really just be the base times height of this rectangle. So it's just a helpful context and remembering what this all means, really. Fourthly, we could say that the integral from a to b of f of x plus or minus g of x, so it's a sum or difference of functions, dx equals the integral from a to b of f of x plus or minus the integral from a to b of g of x dx. So notice the plus or minus corresponding to the plus or minus. The point of this one is really that you can it's kind of like distributing the integral symbol to both functions that follow it as long as they're separated by a plus or a minus. And then fifthly, we could say the integral from a to b of c times f of x, where again c is just some constant, is equal to c times the integral from a to b of f of x dx. So notice what happened here. That c that was written in front of the function in the integrand place was just kind of tossed out in front of the integral. Now, as we'll see in a moment when we get to some more examples, there are some important sums of powers to memorize. So these are sums using the sigma sum notation, which at this point in a calculus class has been reviewed, likely in pre-calculus or college algebra. Let's understand these four important ones that we'll have to end up memorizing for reasons you'll see very shortly in an example. First, the sum from I equals 1 to n of 1 is n. Secondly, the sum from I equals 1 to n of I is the quantity n times n plus 1 in parentheses all over 2. Now, if you distribute this n in the numerator, you can get a secondary form of this, which is really n squared plus n all over 2. Often it's the case that the first forms I'm writing in these are the ones that are more commonly memorized, but I'm going to suggest that you at least write out these secondary forms that like I've written in this second property here, the n squared plus n over 2, because that is going to be more useful for us when we finally start using these things with our definition. Thirdly, we could say the sum from I equals 1 to n of I squared would be, in a first way, could be written as n times n plus 1 times 2n plus 1 all over 6, but that is expanded to be 2n cubed plus 3n squared plus n all over 6. Again, that's going to be a more useful form of it for us. And fourthly, the sum from I equals 1 to n of I cubed is going to be the quantity here in brackets n times n plus 1 over 2, which should be a little familiar. That's the I sum we just talked about a couple times ago here. But now it's that quantity squared. And again, the secondary expanded form of it would be n to the fourth plus 2n cubed plus n squared all over 4. Let's try an example where we use the limit definition of the definite integral to evaluate the following expression. Now, just a quick note about this. When you see something like limit definition or any kind of definition involving the limit of this definite integral, it means you have to go through the full limit to evaluate it. If you think back to derivatives, we started discussing and using derivatives with a limit definition. It was a while ago now, and then you'll recall we didn't stick with that limit definition. We eventually learned some shortcut rules or definitions for common functions. Well, the same will be true in the context of a definite integral. We're just not there yet. So we're starting with the limit definition, and we'll eventually get some shortcut rules for this as well. Let's recall that as we have defined above in our notes, the definite integral from a to b of f of x dx is defined as the limit as n approaches infinity of the sum from I equals 1 to n of this f of x sub I star times delta x. We've seen this notation lately. In fact, let's also write out how we're defining it for convenience. We're going to let delta x be defined as b minus a over n. Now, in this context, for this problem, which I should read here, we have the integral from 1 to 4 of, here our function in the integrand is x squared minus 4x plus 2 dx. So notice that the a and b values are given as the bounds of this integral, which means a is 1, b is 4. So that really means we have 4 minus 1 over n, which is really 3 over n. That's our delta x value. So we'll just kind of note that and be using it in our problem. We'll also write out what x sub I star is. Remember, that's just notation to represent the sample point in the interval we're using to define the height of, as we saw with area, it was the height of the rectangle. Okay, it could be the height of that function in that interval, the ith interval, but we can pick it to be anything we want, and for convenience, we let it be a plus I times delta x, which then for us in this problem will be 1, because that's what a is, plus I times 3 over n. And so we could rewrite that as just 3i over n for simplicity here. So that's our x sub I star value that we'll be using as well. So let's kind of restart and try to put this all together. We were asked to evaluate the integral from 1 to 4 of x squared minus 4x plus 2 dx. And what we're saying is that that equals, by definition here, the limit as n approaches infinity of the sum from I equals 1 to n of, now we said f of x sub I star. Well, we know what f is, and we know what x sub I star is, so we'll just put them together. Remember, f was this x squared, so I'm going to put blank squared for the x squared, then it was minus 4x, so I'll put minus 4 blank, and then it was plus 2. So I'm just going to box that up in some brackets here for a second. That's really just our f of x function, but with blanks instead of x's. But in the blanks, since I want f of x sub I star, I'm going to put our x sub I star value that we've already computed, which is this 1 plus 3i over n. So that's going in all the blanks. 1 plus 3i over n, 1 plus 3i over n, and there it is. Now, of course, we also have delta x to multiply by in the end, which we've computed as just 3 over n, and so we'll tack that on there as well. If we could kind of color coordinate some things here, or at least associate pieces of this formula with the definition, the f of x sub I star we've now put in place, that corresponds with the formula f of x sub I star we have above, and then this delta x aligns with the delta x up there as well in our formula, or our definition of the definite integral. So the point is, we're just piecing things together or substituting. It's really just the notation that can get a little overwhelming, but if you break it down one little piece at a time, hopefully you'll be able to follow how everything's related. So ultimately, this limit is our answer. We just need to evaluate it. So let's just keep this limit going now, and so we really have the limit as n approaches infinity of the sum from I equals 1 to n of, now we're going to expand a little bit what's inside the previous step here. What's in the brackets, which I underlined in an orange color corresponding to the f of x sub I star. If we expand that out algebraically just by like foiling the first term that is squared here, and so on, we'll end up with 1 plus 6 over n I squared plus 9 over n squared I squared minus 4, so now we're distributing this negative 4 into that term, that the parentheses that follow it, so minus 4 minus a 12i over n, and then of course the plus 2 that we had on the end there. So all we're doing is expanding the algebra inside the brackets here, and it should be done carefully, of course, with all the fractions going on. And then let's not forget at the end we have our 3 over n for that delta x value there. If we take a second to combine some of the like terms we have inside this, let's rewrite here as the limit as n approaches infinity of the sum from I equals 1 to n, that just keeps getting rewritten every time, of, now in brackets, if we combine like terms inside our brackets that we have at the previous step, we should end up with a 9i squared over n squared minus 6i over n minus 1 in the brackets. That's just simplifying those brackets, a little arithmetic involved in that. And then don't forget we're multiplying by 3 over n after that. And then next, if we were to distribute this 3 over n into all those terms, let's rewrite yet again. We'll have the limit as n approaches infinity of the sum from I equals 1 to n. Now we would have 27I squared over n cubed, and then we'd have minus 18I over n squared minus 3 over n. Let's rewrite what we have yet again. This time, okay, so we have the limit as n approaches infinity. But this time we're going to use some of the properties of sums or sigmas or series. And you may recall these. We did not review them in these notes, but they are usually available in a textbook, sometimes a pre-calculus textbook. The point is, when you have a sum, you can take any constant in the definition of that sum and throw it in front of that sum. And furthermore, you can distribute the series to all the terms in there that follow it. And so if I do a combination of those two properties that are true of series or sums, then we could rewrite this as the limit as n approaches infinity of. Now, in this first term, I can take whatever does not have the I, which by the way is the variable of the sum. So in this case, the 27 over the n cubed, we're going to treat that as a constant and throw it out in front of the sum. So we now have 27 over n cubed times the sum from I equals 1 to n of, well, the only thing left there would be an I squared. We took the 27 over n cubed and just threw it out in front of the sum. But we're going to do that for all remaining terms. So I'll continue here and say minus, and then we'll do the same thing here where we throw the 18 over n squared out in front of the sum, which is from I equals 1 to n, but then it would be just an I that's left after it. And then continuing on to the last term, we would say 3 over n. Notice there is no I in this definition here. So 3 over n is the constant that could come out front. And then we say times the sum from I equals 1 to n of, really it'd be just a 1 there. Okay, so we're kind of just breaking this down algebraically, but this is the limit we're trying to evaluate. Now, the reason we're doing this is because you should at this point notice some things we defined above. Do you notice all these sums that we have in this step here? That'd be the sum of I squared, the sum of I, and the sum of 1. Those were all defined above as ones we should memorize, right? Look above, you'll see them in our notes. And so we're going to be recalling those and see now why they're so useful. So we want now here, let's rewrite again, the limit as n approaches infinity of 27 over n cubed, that was that first constant we put out front, times, now instead of writing the sum from I equals 1 to n of I squared, we're going to write what that equals in its expanded form. You may recall above that we said that's really 2n cubed plus 3n squared plus n all over 6. So really it's this sum being replaced by this expression, which we'll say C above, because we wrote out that definition above, and that's all we're using here. Well, we'll continue to do this, so let's keep these brackets here for the limit. We'll continue to do this. In the next term it was minus, and then we had this 18 over n squared in front of the sum of I. But then this sum, also seen above, can be replaced by n squared plus n over 2. And lastly, we'll have 3 over n times this last sum, which is really just n. Again, see above for replacements on those. Now this limit should start to be looking much more friendly here. If you think through carefully, this is really just a limit of rational expressions or functions, which is old news for us. So let's rewrite this again as the limit as n approaches infinity of. Now we have all these expressions, but as you may recall, there's a bit of a shortcut to finding a limit of a rational function, and just when you compare the degrees of the numerator and the denominator. So I'm going to summarize this first term as 54n cubed. That's just distributing this 27 inside there, plus, and then it actually doesn't even matter what else we have up there. All we need is that leading term, and that would be over, down below, 6 times the n cubed would be, well, 6n cubed. Now, notice I didn't even write out those remaining terms, because the shortcut to finding the limit, which is where we would typically divide by the highest power of the denominator, the shortcut is that anything but those leading terms will turn to 0 anyway, which leaves us only needing those. If I continue, I'll have, in the same way for the next one, 18n squared over 2n squared. And again, it's really 18 squared plus some other things, but those won't end up mattering. And then minus, really those n's will cancel, giving us just a minus 3 there at the end. Okay, so to apply the limits and the shortcut of them, we really just need the ratio of the leading coefficients here. And so the shortcut would be 54 over 6, which is 9, minus 18 over 2, which is 9, minus 3. And so altogether we'll get a negative 3 value for this. And so that is the value of this definite integral according to the limit definition of it, which you've now just exposed in every detail. Let's do another example where this time we want to evaluate the definite integral from -5 to 5 of x minus the square root of 25 minus x squared dx, but we want to do this in terms of areas. Now the first thing we'll probably want to do here is split this up using our properties of definite integrals that we listed above in our notes. What I mean is we have really actually a difference of two different functions in this. We have an x minus this square root, and so we could rewrite this as the definite integral from -5 to +5 of that first function x, and then don't forget the dx, the variable of integration there, and then minus, and then we say the integral from -5 to 5 of the second function, which is the square root of 25 minus x squared dx. So this is the property we have above where you can split up the integrand if it's a sum or difference of functions. Notice we did that, we kept the bounds of integration the same, and we brought the dx along for the ride in each case as well as we split them up. And let's not forget the minus that was between these functions. It should remain between them, or between these integrals now that we've split it up. Alright, so when we wanted to do this in terms of areas, which is how this was specified in this problem, notice, well then we're not going to use the limit definition here. We want to do some geometric analysis. If we draw some coordinate planes and on them try to put each function, notice the first one was just x. Well, remember y equals x is just a slanted line, and we're only considering this from -5 to +5, so we can put the bounds on here and in fact use those to kind of cut the picture so we know exactly where we're working. We only want between those two bounds for this function. Now observe that these two triangles, the area of which we would be interested in finding for the sake of this integral, this definite integral we're trying to find here, they're symmetrical triangles, but one of them is above the x-axis and one of them is below the x-axis. Which means to the left of the y-axis, this value would actually turn out negative, and to the right of the y-axis, that area value would turn out positive. And notice what happens. When the value of each of these match, and yet one's positive and one's negative, then they'll just cancel out to turn into nothing. Which means you would, if computing the area of this function over this interval, you'd get a value of 0, which doesn't really make any sense. An area shouldn't be 0, right? Well, it's because of the negative values here, and that's why we have to restrict those functions from being greater than or equal to 0 when we're talking about the area under the curve, as we said above. If we go on to the next piece, you'll notice that this value of square root of 25 minus x squared, that would be, if we look at it, the top half of a circle. You'll recall that x squared plus y squared equals 25 would be the equation of a circle centered at the origin with radius 5. And so we can go ahead and draw that, except if you were to try to solve that for y, you'd normally get y equals plus or minus the square root of 25 minus x squared. As you may recall, the plus or minus shows up when you take the square root of both sides. But in this function, notice it's only written as a positive, which means it's only the top half of the circle, which means we really want to find the area of this semicircle here. Well, let's recall that area of a circle is pi r squared, and of course r here is 5. But then since we really only want half of this circle, since it's the top half only, we would need to divide this by 2. So really we have 25 pi over 2 as the value of that area. Of course, it's all positive above the x-axis there. So we can summarize our definite integral in terms of areas by knowing the first term we had split up turned into just 0, then we had minus, and then the second term, which was the semicircle, that was the 25 pi over 2, for an ultimate value of this definite integral of negative 25 pi over 2.